When we observe the universe at its absolute extremes, from the crushing cores of black holes to the explosive birth of the cosmos, our mathematical models hit a wall. For decades, we have relied on two separate pillars of physics to explain how reality operates. The first is general relativity. This is Einstein's framework for the macroscale universe, where gravity operates as a smooth, continuous fabric of space and time that bends under the weight of massive objects. The second pillar is quantum mechanics, which governs the microscale universe. At the level of atoms and subatomic particles, reality is not smooth at all. It is discrete, jittery, and divided into rigid, pixelated bursts of energy. The tension arises when these systems are forced to overlap. If you try to calculate the gravity of a tightly packed quantum object, the mathematics break down. The smooth geometry of relativity clashes against the grainy nature of quantum mechanics, resulting in impossible, infinite values. To resolve this, theoretical physicist Nathaniel Faxon-Sharir introduces a framework in his book, My Dear Universe, called Quantum Hard Foam and Entanglement Theory. QHFET introduces a novel structure designed to merge spacetime, matter, and non-local particle behavior into a single system. This unification reveals the literal mechanism governing how rigid, subatomic units assemble into the seamless universe we experience every day. To see how this construction works, we have to scale down past atoms and subatomic particles to the Planck length, the absolute smallest measurable distance in the universe, roughly 1.6 times 10 to the negative 35th meters. At this scale, QHFET proposes that spacetime is not an empty, continuous void. It is composed of quantum hard foam. These are discrete, indivisible units, or foam cells, that act as the structural pixels of reality. The theory then introduces entanglement. In quantum mechanics, particles can become entangled, meaning they share a connection where the state of one instantly dictates the state of the other. This instantaneous communication ignores physical distance entirely, defying our classical understanding of space. You can visualize this connection like a specialized shirt. If you pull the collar, the bottom hem lifts at the exact same moment. The fabric knows it moved, responding as one unit, without waiting for a physical ripple to travel down the material. Because this connection ignores local distance, entanglement is interacting directly with the global architectural structure of the universe, bypassing the limitations of standard physical space. This brings us to the core mechanism of QHFET. These non-local connections actively manipulate the physical size and structure of the space-time foam cells. This equation shows the relationship. Foam cell size, delta, is a direct function of the entanglement operator, psi. As entanglement changes, geometry adapts. The alpha constant measures how strongly a particle warps the cell. The beta constant measures the foam's natural stiffness, resisting the pull. At the microscopic level, these cells are rigid, but we must account for what happens when trillions of these entangled foam cells face the massive compression of a planet or a black hole. Under extreme gravitational pressure, these cells undergo a phase transition. The crushing weight forces the discrete units to melt into a unified, continuous fabric. By identifying this phase transition, the math finally aligns. Discrete quantum mechanics literally compress into the smooth, continuous geometry demanded by general relativity. Scaling back up to a cosmic viewpoint, we now have a framework where the smallest subatomic interactions and the largest gravitational bodies belong to the exact same continuous process, operating flawlessly across scales. This solves lingering mysteries like the black hole information paradox. Because entanglement physically dictates the shape of the spacetime foam, the information held by those particles is preserved in the geometry of the fabric itself, even under infinite gravitational compression. By calculating how the entanglement operator, psi, influences foam cell size, engineers can maximize quantum parallelism. This provides a physical map for next-generation processors to move information through spacetime with unprecedented efficiency. This structural control extends to global security. By manipulating the beta constant, the stiffness of the foam itself, we can stabilize non-local connections over vast distances. This makes super-dense data coding and impenetrable quantum cryptography a physical reality rather than theoretical. By defining the universe as a dynamic, phase-shifting foam bound by entanglement, we elevate our grasp of reality across the cosmic, quantum, and principal layers of existence. To explore more of these cosmic, quantum, and principal theorems, return to MDU. Please like and subscribe.